In this example, we're asked to determine whether the given functions are linear, exponential, or neither. And then for those that are linear or exponential, we want to find a corresponding function that models that data. So we're given tables of values that you might see in your graphing calculator if you entered a function into your graphing calculator. So let's look at the first one. So remember, with an exponential function, as x increases by 1, each of the y values are growing by the same factor. So if I look at the y value, so as x is increasing by 1 here, if I look at my first y value, my first g of x value, I have 2. So then as I go to the 5, if you look at each of these, then 5 to 8, 8 to 11, 11 to 14, we're actually not multiplying anything, we're actually adding. So as we add 3 here, add 3 each time. So if we're adding the same amount every time, that means it's not going to be exponential, it's going to be linear. So we know this is linear, and that's because we're adding the same number each time x increases by 1. So we know it's linear, again, because they're not growing by a same factor each time, they're growing by the same constant number, 3. So that constant number, that's actually our slope. So we can write our equation of our line, our mx plus b. So we see our slope is 3, and our y-intercept, we can see from the table, is 5. So the equation of that linear function is y equals 3x plus 5. Okay, let's look at b. So if I study all of these h of x values, these y values, I've got 1/4, 1, 4, 16, and 64. So here, if we look closely, as I move from 1/4 to 1, I'm multiplying by 4. Well, same with going from 1 to 4, I'm multiplying by 4. And 4 to 16, I'm multiplying by 4. And 16 to 64. So since these are growing by the same factor of 4 every time, we know that this is exponential. So this is an exponential function. And that's because we're multiplying by the same number. Multiplying by the same number each time x increases by 1. Okay, so to come up with the equation of this function, remember the general form of an exponential function is that y equals c times a to the x power. So that c, remember, is the initial value. That's the value of the function when x is 0. So according to this table, that would be a value of 1. So we can say our c is 1. And then our base, the a value, the base of the exponent is the growth factor, the factor by which the h of x values are growing as x increases by 1, and we can see that that's 4. So our a value is 4. So we can fill in then our function is y equals 1 times 4 to the x, which is just 4 to the x. So the equation of our exponential function here is 4 to the x. Okay, part C, if we study these g of x values as x is increasing by 1 each time here. So if you study this pattern for a second, as you go from 6 to 1, you could say we're subtracting 5, or we could say we're multiplying by a 1/6. But then when we go from 1 to 0, we're either multiplying by 0 or subtracting 1, and you can see there's no pattern here within all these values. So if you can't identify a consistent pattern of numbers being added or subtracted, or multiplied or divided, then that means it's neither exponential nor linear. So this is neither, and that's because there's no pattern in the g of x values.